functions have inverses. So there's going to be 12 new functions that you learn, and each one of those 12 functions has a derivative. So it's going to be a total of 24 new functions. But that'll be at the very beginning of Cal 2 usually. We say, hey, now we introduce you to the hyperbolic trig. Here they are, here are their derivatives, here are their properties, and then we move on. We're not going to do it here. Okay, so 4.7. 3.7, sorry, 3.7. 3.7 is called this. Now, I've heard it pronounced many different ways. La Hospital is one way I've heard it pronounced. But the way that most people will say it is L'Hopital. L'Hopital. We're going to learn this thing called L'Hopital's rule. And this rule is just so awesome, all right, that it's hard to really appreciate how great this rule is, all right? So let me give you something to think about, all right? Way back in the beginning of this class, before we were even doing derivatives, we were doing limits, and there was this very special limit that I showed you, and I told you that this limit's 1. And it was that whole sign junk over junk problem. Remember that? And I said, this limit is 1, and there was no way for me to prove it to you, right? I said, there's not an easy way for me to prove it. If you want me to prove this to you, you can come by my office. I can show you this really, really, really beautiful geometric proof. And I told you, nobody really has ever come by to look at that or to ask me about that, and that still holds today. Nobody has asked me to see this proof geometrically, all right? But you took it on faith, right? And I did also tell you back then that we will get to a point where I'm going to give you something where this is going to be very easy. And I'm going to be able to, I guess, prove it to you easily. But you have to believe in what's called L'Hopital's rule, which is something that has been proven. I'm not going to provide the proof for the L'Hopital's rule. I'm just going to give you the rule. Right? So here's what L'Hopital's rule says. We'll get back to this. L'Hopital's rule says this. Let's say you're taking a limit. All right? Let's say you're taking some limit. And so we're talking about limits again. I should preface all this. We're going back and we're looking at limits again, which I know you all didn't like limits, but we're going to look at them again. It says if you're taking a limit, and it actually doesn't matter what is going to what. So you could have x going to infinity, x going to 0, x going to 4. Who cares about what the limit's actually doing, right? Like going to. And then what you have here is a quotient. That means you have something over something, all right? So L'Hopital says if you've got this limit set up, and that limit goes to 0 over 0. What did we usually say whenever that happened in the very beginning of this class? 0 over 0 meant what? It's bad, there's more work to be done, right? We had to do some algebra, some tricks, something, right? That's what we used to say. L'Hopital's rule says, look, if you ever see this, and you have 0 over 0, here's what we're going to do. Then, try this limit. Those are derivatives. So if you're ever doing a limit and you're getting 0 over 0, do this limit instead. What's the difference between this limit and this limit? Well, you're going to take the derivative of the top and bottom separately. You're not going to do a quotient rule. You're just going to take derivative of the top and bottom, and then you're going to look at that limit, and maybe that limit's easier. All right? And it says that when you try this one, if this equals some number, right? If you get L, right, some answer, L, then that's that answer as well. Right, so whatever this answer is, it's that answer as well. Now, in my notes, I have it written a little different. I'm just trying to get you to get an idea. In my notes, here's what it looks like. So if you, it's right on top of it. So it says, hey, if you're ever taking a limit and you're getting 0 over 0, then that limit that you're trying to find, right, that's giving you 0 over 0, will be equal to the limit of the derivative of the top over the derivative of the bottom. It's an awesome rule. I mean, it's really awesome. All right, let's check it. Let's do it for this problem right here. Let's do that limit. All right, so we take this limit right now. What happens when we plug in 0? Sine of 0 is 0 over 0. This is 0 over 0, right? Normally that's algebra, do a trick, do something, right? But now I can bring in this rule. So what I'm going to do is I'm going to say this is equal to, and then I need to tell you I'm using L'Hopital's rule right now. I need to do something that lets you know that I'm using L'Hopital's rule. And there's different books do it different way, different authors do it different way. Some books, they put an H there to let people know they're using L'Hopital's rule. Sometimes they'll put an H with a circle. Sometimes they'll put an L. Sometimes they'll put an L with a circle. It's just something that lets the person who's looking at the work know that L'Hopital's rule is about to be applied. What I do, is the L with the circle. Sorry, I had that one there. That's the one I do. I think our textbook uses an H, all right? So that's telling you that I'm about to use L'Hopital's rule. So I'm going to keep the limit exactly the same, but now I'm going to take the derivative of the top, which is cosine x, and divide that by the derivative of the bottom. What's the derivative of the bottom? 1. Do you see that I did not do the quotient rule there? L'Hopital's rule does not say do the quotient rule. L'Hopital's rule says do the derivative of the top and bottom separately. And now try the limit again. If x goes to 0, what's cosine of 0? 1. Okay, and then 1 is just 1, right? We're just letting x go to 0, but 1 is just 1. So this goes to cosine of 0 over 1, which is 1 over 1, which is 1. And that is the answer, right? I told you that's what the answer is. That's the proof that the answer is 1, but you have to believe L'Hopital's rule, all right? Let me give you another one. So what about this? This is one that we did way back in the beginning as well. One of the first problems I ever probably gave you was something like this. Look at that one. Let x go to 2. What do you get on top? 0. What do you get on the bottom? You have 0, 0, right? That used to mean algebra and trick. Do y'all remember what algebra we would do here? Factor, right? Difference of squares on top, you get something to cancel? Yes? Okay, I'm not even going to think about that anymore. I'm just going to go straight to L'Hopital. Okay, and I take the derivative of the top. What's the derivative of the top? 2x. Derivative of the bottom? 1, okay. Now, plug in 2 again. What do you get? 4. That's your answer. Now, if you want to just see, this is the way we did it back in the day. We factored the top and bottom, difference of squares. Oh, I don't know why I put a 4 there. Right, difference of squares on top. And then we cancel these two factors, right? And then we let x go to 2, and what will we get? 2 plus 2, we get 4. Right? Isn't that nice? Let's do another one. How about these? You loved these. I had people sending me like emails and texts saying, could you please put more of these on tests for us? Do you remember what we had to do here? Yeah. Where you had to rip it all apart and then like say, oh, it'd be really nice if we had a 3x down there, and then we would just make it appear and slide things around. Remember all that? Complete disaster. All right, let's check. What happens? X goes to 0. 5 times 0, 0. Sine of 0, 0. Okay. 3 times 0, 0. Tangent of 0, 0. How do I know tangent of 0, 0? Because I know what the tangent function looks like. And I know add 0 goes through 0. Okay, so I am getting 0 over 0, right? Fine. I'll use L'Hopital's rule. So I use L'Hopital, limit, x goes to 0. Okay, derivative of the top. Be careful. Derivative of the top. cosine of 5x times 5, right? Chain rule. You still have to do the chain rule on top, right? The derivative sine of something is cosine of it times the derivative of what's inside, which is 5. And then on the bottom, you have to take derivative of tangent. Derivative of tangent is secant squared of 3x, then chain rule, times 3. And now try it again. Try it again. If x goes to 0, 5 times 0 is 0. What's cosine of 0? 1. So this is going to turn into a 1. 1 times 5 on top. And then on the bottom, okay, this is a little bit more tricky. What is secant of 0? Well, that's the same as 1 over cosine of 0, isn't it? That's the reciprocal. So that's still 1, isn't it? Right? Secant of 0 is the same as 1 over cosine of 0. So when I put 0 in here, I get secant of 0, which is 1 over cosine of 0. That's 1 over 1. And then I square it. What's 1 squared? 1. So that's all a 1 right there, right? And 1 times 3 is 3. Wasn't that a lot better than ripping it all apart? Yes.
What happens if you apply L'Hopital's rule to something that doesn't equal 0 to 0?
Okay, so this L'Hopital's rule only works when you have 0 over 0. It's only valid when you have 0. Well, we're going to see it works in other cases too. There's only 2 cases it works in, though. It works when we have 0 over 0 or infinity over infinity. So you can't. If you do it when it's something else, you're breaking the rules. Am I answering your question? Okay. All right. So I kind of lied to you a little bit. Not lied, but I haven't revealed everything. L'Hopital's rule works when you have 0 over 0, but it also works when you have either positive or negative infinity over positive or negative infinity. So I'm going to go back to my notes here. So I just said here in this note that if you're taking a limit and you ever get 0 over 0, then use L'Hopital's rule and just take derivative of top bottom and see what that gives you, right? The next part of L'Hopital's rule says, hey, good news. It works also if you take a limit and the top or bottom go to positive or negative infinity. So if the top goes to positive infinity, bottom goes to positive infinity, you can use L'Hopital. If one goes to positive and the other one goes to negative, you can still use L'Hopital. Doesn't matter what order. All right? And you do the same exact thing. You take derivative of top and bottom, and you see what happens. So let me give you an example of that one. Let's see if this rings a bell. Limit x goes to infinity. Let's go with x to the third plus x plus 1 over 5x to the third plus x squared plus x. Yeah, there we go. A lot of x's, yeah. All right, so if I say take this limit, let x go to infinity, where does my numerator go? Infinity cubed plus infinity plus 1. The top's headed to infinity, right? The bottom? Also headed to infinity. Do you all remember what we did when we had this scenario before?
Multiplied by the greatest denominator.
We would look at the highest power that we see in the denominator, right? X cubed. And I'd multiply 1 over x cubed, 1 over x cubed here. Remember that technique? And distribute it through? No more. L'Hopital. So here, I'm bringing in L'Hopital. Limit x goes to infinity. What's the derivative of the top? 3x squared plus 1. Derivative of the bottom? 15x squared plus 2x plus 1. Okay, now, do the limit again. What do you get this time?
6x over...
Oh, careful, it's going to infinity.
So infinity over infinity.
You still have infinity over infinity, don't you? So guess what L'Hopital says? You can keep going. As long as you have 0 over 0, infinity, infinity, you can keep going. So I'm going to use L'Hopital second time. All right, I should be pointing out here, that this one's giving infinity over infinity. This one is giving infinity over infinity. So I'm applying L'Hopital second time. Limit x goes to infinity. What did you say? 6x over 30. 30 plus, not 30, 30x plus 2. And we get infinity over infinity again, don't we? Big deal. We're going to do L'Hopital again. Do y'all see what's happening each time we're doing L'Hopital? It's like we're chipping away at the powers, aren't we? And so on the next application of L'Hopital, we get limit x goes to infinity, 6 over 30, which is 1/5, which is the answer. If you were to do it the way we did it before, where you came in with that highest power on top and bottom, you would have got that same answer. Pretty nice, huh? Pretty nice. Most students love L'Hopital when they learn it the first time because they're like, whoa, this is really cool. So, well, I wouldn't say love, but they like it. So let me ask you something, because students will ask me this. Why not show you all this before? You know, like, why make you suffer through all these limits? Why did we torture you with all the limits first?
Is it like stacking a cake? Like,
So, like, making you learn this stuff to build the foundation? In some way, yes.
So that we understand like the why and not just the how.
Why and not how? Sure, right. Instead of just giving you some formula and you have no idea what's going on, right?
was it to see what the calculator is doing?
Any other ideas of why I didn't give this to you before?
So that we can appreciate the shortcuts.
So you can appreciate it? Yeah, sure. It's a shortcut, right? The reason I didn't give it to you before is because I couldn't. Why couldn't I? Because you didn't know what? You didn't know what a derivative was. Right? So if I would have said, hey, see how we're getting infinity over infinity, and then I would have told you, go find the derivative, we hadn't defined what a derivative is yet, right? So you would have been like, do what? You know, like, so when you think about calculus, I told you all this before. Oh, that's cute. The limit is the heart of calculus, all right? What's wrong with the heart? It's a good heart. All right, the limit is the heart of calculus. Everything is born from this limit, all right, idea. And one of the ideas we have is the derivative. Remember, the derivative of a function is just a limit. It's the limit as h goes to 0 of f of x plus h minus f of x all over h, right? And then we find out there's all these little shortcuts to do that, right? But this is just one application of the limit. That's just one thing you can do with the limit. What a mathematician named L'Hopital figured out was that you can actually use this derivative idea to actually go back and do limits again. So back in the day, we had no idea what that was, but now we can use that as a tool to solve these, which is pretty cool, right? It's like we had to create something to help us go do this, right? I need to go back and check my math history because I don't recall this right offhand. But if I'm not mistaken, L'Hopital, I might be wrong on this. Someone's going to have to look this up if you actually care. I believe L'Hopital was not the person who actually came up with this. My memory is failing me. This might not be it. I might be thinking of something else. It might be Pascal's triangle I'm thinking of. But anyways, there's a lot of times in math what happened back in the day, back, centuries ago when humans were trying to figure shit out. It would be like an artist. You know how right now you can commission an artist to like give you some, like make a sculpture for you? Right? Like businesses will hire an artist, hey, can you do a mural on this wall? Okay, back in the day, wealthy people would hire mathematicians to try and solve problems that people hadn't figured out yet. And say, it's like, hey, I'm going to pay you. You go try and figure this shit out because you're smart with math, right? If you figured it out, it would be my name on it because I paid you to do it.
What? So it was him who figured it out.
It was L'Hopital?
But he purchased the formula, like.
That, okay, so this is it then. Yeah. So L'Hopital basically bought this formula and his name is on it. And that happened a lot. I mean, back in the day, I mean, people would sit there and do math and they get paid by somebody and they would not get credit for it. It happens today, right? Right? It happens today. You come up with something. If someone really likes it, they'll go buy it from you. Now it's not yours anymore, right? So, anyways, it's a great rule. Now, it has limitations, all right? I don't want you to believe that L'Hopital is like the magic pill, all right? That's going to solve all limit problems. I'll give you an example. Limit x goes to infinity of x plus 1 over the square root of 4x squared plus 1. What do we get here if we let x go to infinity? Infinity over infinity, right? We get infinity over infinity. So you're like, hey, L'Hopital, right? You're all happy, skipping down the hallway. Derivative of the top. 1. Oh, that's beautiful. Okay, derivative of the bottom. Well, it's the derivative of the square root of something, right? What's the derivative of the square root of something? 1 over 2 roots of that something, right? Times the derivative of what was in there, which is 8x, right? Okay, now I clean that up, right? If you clean that up, this and this go away, you get a 4 there, right? You with me? And that's 1 over a fraction, right? So I can flip it. So this becomes limit x goes to infinity. I've got square root of 4x squared plus 1 on top, and on the bottom I have 4x. And you still have infinity over infinity, right? Do y'all see what I did there? It's just 1 over a fraction, so I flipped it. Okay, so I have infinity over infinity, so I'm like, okay, I'll break out L'Hopital again. All right, so here comes L'Hopital a second time. Limit x goes to infinity. Derivative of the top is the square root again, right? So I'm going to have 1 over 2 square roots of 4x squared plus 1 times derivative of what's inside, 8x all over 4, right? Derivative bottom. All right, what happens up top? That becomes a 4, right? And I can actually kill this 4 and this 4. But what do I still have? Almost. You have something more than 1 up top. What do you have up top? That x is still there, isn't it? So you have x over the square root of 4x squared. Seems like we're not getting anywhere, right? Yeah, oh, yeah, all we did was got rid of the 1. But see, it's never going to get better because every single time we do this derivative, what are we going to get? 1 over root, blah, 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 and then 8x. And that's always going to be a fraction, right? And then look what's going to be on top. We're going to get a 1. So it's just going to keep on just... So it's not the magic pill. It works a lot of times, but there are some cases where it doesn't work, all right? We good? Okay, let's take a break. 2:30, let's take a break. We'll come back in, let's say, about 11 minutes, 2:40. And we're going to do more L'Hopital. Because as great a tool it is, we have to blend it with some other ideas now, all right?